You think you know what big means. A skyscraper, a mountain, a continent, maybe a planet. But the moment you leave Earth, the word big loses its grip. The universe contains objects that make our planet look like a dust mote. Objects so large that light itself takes hundreds of millions of years to cross from one side to the other. And the strangest thing about these objects is not their size. It is that we have actually measured them, and the measurements have held. In the next 12 minutes, we walk up the cosmic ladder of size. From your living room to the largest known structure in the observable universe, we use only confirmed measurements from peer-reviewed astronomy. No speculation, no exaggeration, no short-style hype. Just the actual numbers and the moment-by-moment realization of what they mean. Start with Earth. 12,700 kilometers in diameter. Now the Moon, 3,400 kilometers across, orbiting at a distance of roughly 384,000 kilometers, about 30 Earth diameters away. Already our intuitions begin to slip. Most people picture the Moon close to Earth. It is not. You could fit every other planet in the solar system, edge to edge, in the gap between Earth and Moon, and still have room left over. Now, the Sun. Diameter, 1.39 million kilometers. That is 109 Earths laid edge to edge across its face. By volume, the Sun could swallow 1.3 million Earths and still have room. And yet, on the cosmic scale of stars, our Sun is unremarkable. A yellow main-sequence dwarf, slightly above average mass, halfway through a 10 billion-year hydrogen-burning lifetime. The largest known stars dwarf the Sun in ways the human mind genuinely cannot picture. UY Scuti, a red supergiant in the constellation Scutum, has a radius about 1/700 times that of the Sun. If placed at the Sun's position, UY Scuti would swallow Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, and reach roughly out to the orbit of Saturn. Stephenson 218, an even larger candidate red hypergiant, may extend nearly to Uranus. But stars are not the largest single objects. Black holes are. A typical stellar mass black hole formed from a collapsed star might be only 30 kilometers across, astonishingly small for so much gravity. But the supermassive black holes at the centers of galaxies operate on a different scale entirely. Sagittarius A, the supermassive black hole at the heart of our Milky Way, is about 4.3 million times the mass of the Sun. Its event horizon spans roughly 24 million kilometers, a volume larger than the Sun itself. Now consider TON 618, a supermassive black hole at the center of a distant quasar. Its mass is estimated at 66 billion solar masses. Its event horizon stretches roughly 1,300 astronomical units across, about 13 times wider than the entire orbit of Pluto. A single black hole that, if placed at the Sun's position, would extend its event horizon nearly halfway to the next nearest star. Our Milky Way galaxy is roughly 100,000 light-years across, contains somewhere between 100 and 400 billion stars, and is itself rotating slowly around its central supermassive black hole. Light, traveling at the universal speed limit, takes 100,000 years to cross our galaxy from one side to the other. Now zoom out further. The Milky Way is part of the Local Group, a small cluster of about 80 galaxies bound together by gravity, spanning roughly 10 million light-years. Andromeda, our nearest large galactic neighbor, sits 2.5 million light-years away. The Local Group, in turn, is part of the Virgo Supercluster, a sprawling structure of about 100 galaxy groups extending across roughly 110 million light-years. In 2014, astronomers led by Brent Tully at the University of Hawaii defined an even larger structure encompassing the Virgo Supercluster, Laniakea, meaning immeasurable heaven in Hawaiian. Laniakea contains approximately 100,000 galaxies and spans 520 million light-years. It is the largest gravitationally connected structure we currently inhabit. Beyond Laniakea, the universe arranges itself into what cosmologists call the cosmic web, a vast network of filaments, walls, and sheets of galaxies separated by enormous voids. The largest individual structures detected within this web push the limits of what we thought possible. The Hercules-Corona Borealis Great Wall, identified in 2013 by Istvan Horvath, John Hakila, and Zsolt Bagoli using gamma-ray burst data, may stretch as much as 10 billion light-years across, almost a tenth of the diameter of the entire observable universe. If real, it is so large that its existence challenges the cosmological principle, which says the universe should look statistically the same in every direction at very large scales. Other contenders include the Sloan Great Wall, about 1.4 billion light-years long, discovered in 2003 in Sloan Digital Sky Survey data, and the Boss Great Wall, identified in 2016, comprising at least 4 superclusters spanning 1 billion light-years. Each of these structures should not exist according to standard cosmological models. The fact that they do is one of the most important open puzzles in modern cosmology. And finally, the largest object we can talk about with any precision: the observable universe itself. A sphere centered on Earth with a radius of about 46 billion light-years. Its diameter, 93 billion light-years. Inside it, an estimated 200 billion to 2 trillion galaxies, each containing hundreds of billions of stars. This is not the whole universe. It is only the portion from which light has had time to reach us in the 13.8 billion years since the Big Bang. The actual universe extends further, perhaps far further. Some inflationary cosmology models suggest the entire universe is at least 1023 times larger than the observable region. Others propose it is genuinely infinite. Either way, we are very small. The largest scale we have measured is 93 billion light-years across. The smallest objects we have studied are far below the size of an atom. Between these two extremes, fitting in a thin band of complexity and warmth, is everything we have ever known. Scale in cosmology is not just a number. It is a discipline. A reminder that human intuition, evolved for the size of savannas and the time scale of seasons, fails completely once we leave Earth. Every honest cosmological number is a stretching of the imagination. And every measurement that holds is a reminder that nature does not care about what we find unbelievable. If you love careful evidence-based exploration of the universe at every scale, subscribe to Cosmic Edge. We follow the measurements to where they get genuinely vast, and we are honest about what we do and do not yet know.